Have you ever thought how a quantum processor can be verified when it accurately performs complex computations than a classical computers can't? That is what we are going to learn today. I'm your Sue and this is Hello AI. Researchers from MIT, Google and others have redesigned a novel method for verifying when quantum processors have performed complex computations that classical computers can't. They validate the method on a custom system that can able to capture how accurately how a photonic computed notoriously difficult quantum problem. Quantum chips perform computationals using quantum bits called qubits that can represent two states corresponding to classic bits, a 0 or 1, on a quantum superposition of both states simultaneously. Full-scale quantum computers will require millions of qubits, which is not yet feasible. That's why noisy intermediate-scale quantum chips, NISQ, which contain 50 to 100 qubits, are enough to demonstrate quantum advantage. Means NISQ can solve certain algorithms that are intractable for classical computers. These chips can perform operations expected, but there is a chance that can be inefficient. They do a divide and conquer method. The researchers work essentially on traces of quantum stable generated by the quantum circuit back to a known input. Doing so reveals which circuit operations were performed on the input to produce the output. Those operations should always match the researchers programmed. If not, the researchers can use the information to pinpoint where things went wrong on the chip. At the core of the new protocol called variational quantum unsampling lies a divide and conquer approach that breaks the quantum state into chunks. Instead of doing all the whole thing in one shot, which takes a very long time, they do the unsampling. They scramble it layer by layer, which is very efficient. This computation is inspired by QNN, which is quantum neural networks. We are not going to finish this learning today. We can see how they did it with a super detailed technical information in the coming days. Hope you find this interesting, and this is just an introduction of what they are doing and this research, and we are going to continue it in the coming days. And that's all for today. Bye bye. Life is either a daring adventure or nothing at all. Helen Keller. Just a recap, yesterday we learned a researcher's work essentially traces an output quantum state generated by a quantum circuit back to its known input state. Today, how they are doing it exactly. I'm your Sue and this is Hello AI. To run the QNN, they use a traditional silicon fabrication technique to build a 2 to 5 millimeter NISQ chip. As I said, NISQ is Noisy Interpretation Scale Quantum Chip, with more than 170 control parameters, tunable circuit components that make manipulating the photon path easier. Pairs of photons are generated at specific wavelengths from an external component and injected into the chip. The photons travel through the chip's phase shifters, which change the path of the photons, interfering each other. This produces a random quantum output state which represents what would happen during the computation. The output is measured by an array of external photodetector sensors. The output is sent to QNN, which is a quantum neural network. The first layer uses complex optimization technique to dig through the noisy output to pinpoint the signature of a single photon among those scrambled together. Then it unscrambles that single photon from the group to identify what circuit operations return it to its known input state. Those operations should match exactly the circuit's specific design for the task. All subsequent layers do the same computation, removing from the equation any previously unscrambled photons until all the photons are unscrambled. As an example, say the input state of qubits fed into the processor was all zeros. The NISQ chip executes a bunch of operations on the qubits to generate a massive, seemingly random changing number as output. An output number will constantly be changing as it is in the quantum superposition state. Then layer by layer it determines which operations revert each qubit back down to its input state of 0. If any operations are different from original planned operation, then something went wrong. Researchers can inspect any mismatches between the expected output to input state and use that information to tweak circuit design. Not over yet. Tomorrow we see how they did that boson unsampling experiment using the new method of validation. That's all for today. But I have this request for you guys that summer is soon, so let's help the birds and animals with water. Kindly remember to keep a bowl of water before your house or in the garden where animals and birds can satisfy the thirst. Hope you liked it. Let's see with the boson unsampling today. Bye bye.